what we were doing is talking about the Hamilton free energy Ginzburg-Landau, which is ddx m square by 2 phi square plus half grad phi square plus lambda over 4 phi 4 for the scalar field. And we were in the process of doing a scale transformation, removing the momentum components between lambda over b and lambda, right? And do a rescaling. So we did when we do the first step, so if we write this in terms of m square over 2 plus p square over 2 phi p phi minus p plus lambda over 4 d3p1 by this is d, this is d, this is d, this is d, ddp2 divided by 2 pi d, ddp3 divided by 2 pi d, phi p1, phi p2, phi p3 minus p1 minus p3, right? And the first task was that integrate out that part, integrate out lambda over b to lambda, these p's over here, and see how it changes the coefficients over here. First you do that, integrate out this, then rescale momenta to ensure cutoff is lambda again, so that I can repeat the step, and then you rescale the fields so that the coefficient of p square phi p minus p is half once again. So this is always going, we want it always to be half, to do a rescaling which keeps it at half. That is, which is essentially saying that this p square is not going to change, so you are going to rescale the fields in such a manner that the coefficient of p square is unchanged. So we do that, and then the new Hamiltonian looks like m squared. So new Hamiltonian, m squared goes to some m prime square, and we obtain m squared equal 0, and then we add on. This is, and then it is m prime is m squared over 2 into this 2 over here plus 3 lambda over 2 integral ddp over p square plus m square whole square lambda over b to lambda. So that's where we are, that's for the m part. So the m prime square is 2m squared, that is for the Gaussian model. We are working with only this part of it, then it is m prime square equal to 2m squared. If you go ahead and if you go ahead and work with the include the other part, then it is going to be 3 lambda plus 2 squared over here. So it is m prime squared is 2m squared plus 3 lambda integral ddp whole square. Right. So that's our that's the way things were. If this is not there, then the Gaussian index is nu equal to half. So all right. Now we go to lambda squared. So you go to the next term that is there. And what we looked at is the correction to this term over here. We have not, mind you, looked at the correction. We did not, in the analysis that we carried out, we did not look at the correction to this coefficient over here. We simply looked at this part over here, and we had the contribution which you have two of these, and then you connect this to this, and you connect this to this, which over here the picture was that lowest order this, and then the correction which is this. Over here the lowest order is this, and then the correction which is this. And this is lambda over 4, and then this one over here, so it is lambda over 4 minus lambda over 4 squared coming from these two chaps over here. Then there is 9, which was the combinatorial factor of this with this. And then we had ddp, so it is p square plus m square whole square. Each of these lines are p square plus m square, so each line over here is 1 over p square plus m square. So 2 lines over here, only 1 line, and therefore so 2 vertices over here, and then we had this, which is going to become define a new coupling constant, which is equal to, let's say, lambda prime over 4. All right, and this part over here, the integral goes from lambda over b. This should have been it was 36, right? I mean, this part over here is has a 9 into 4.
So another thing,
there will be a
for d in lambda. 4 minus d into lambda. It's the first term.
Oh,
dimensionality term.
Oh, there should have been a b. Yes, right. You are absolutely right. This had a b into, it is 4 minus d, right? Yeah. And this one had a b square, which is the 2 over here. Right. So this is actually, it is m prime square is b square times m square, and b square works out to be 2. And over here, we are the scaling is 4 minus d. This part over here comes entirely from the fact that sorry, it's b square. Right. sorry, it's not, it's b square. So this one transforms as m prime square equal to b square m square. This transform as m prime square by 2 is b square by 2 into m square by 2 plus 3 lambda over b. This over here is the first term is lambda 4 minus d, that coming from the second step over here when I rescale, removing the momentum components this, and then rescale to make coefficient of grad phi, right? Yeah, grad phi square over so that's just 1. So you make sure no change over there, and that's what makes this m square go to m prime square times b square over here. All right, yeah. So that's the 3 processes, removing the momentum components, rescale to make coefficient, rescale twice, that is rescale once to restore cutoff, removing restore cutoff, there is restore cutoff by scaling the momenta, rescale the fields to, yeah, right. So those were the 3 procedures, and this is b square and this. And why is nu equal to half? Nu is half because I do a scale transformation, then the xi at b times m, so b square times m square is smaller than m square over here by a factor of b, and therefore I do this repeatedly. Xi m square is equal to b to the power n. So I have done, and then it is xi to the power b 2n m square. I go large m, so that m square large n, that is xi to the power 2n, is equal to 1. So that's what is this over here? It's b to the power, it is b, sorry, it is b to the power, so xi m square is b xi of b square m square, and I go n steps, and it is what I want to do is set m square b square, so it is this is b square m squared xi at m squared, this is down by this, and the new m prime square, which is m prime square b square, and that is this. Then you go repeat if you go bn times, then it is xi b to the power 2n m square, right? And what you do is you set, so you want this to become 1, so b to the power n 2n. 2n m squared is equal to 1, b to the power 2n is 1 over m squared. So your n is equal to log of 1 over m square by log of 1 over b, and that is what this n is, and xi m square. So this is equal to 1. Yeah, this is equal to 1, and trying to keep the board space minimum. So xi to the power m square is like b to the power n. So xi and b to the power n, and I have got b to the power 2n, b to the power 2n times m square has been set equal to unity, and therefore xi m square is equal to b to the power n times xi m square. This I don't want here. That's xi m square is, let's write this out, is b times xi of b square m square is equal to b to the power n xi of b to the power 2n m square, and that is, choose n so that this is equal to 1. So xi m square is like b to the power n, and n over here 2n b to the power 2n is like 1 over m square. So b to the power n is it's n log b square. I want to transform. So this is b to the power n, which I want to transform to m square. So this is 1 over m square to the power half, right? B to the power n, which should be like 1 over, because b to the power n is like 1 over m square. B to the power 2n is like 1 over m square. So b to the power n is like 1 over m square to the power half. So I have it right. 1 over m square is like t minus tc. So xi diverges as t minus tc. So 1 over t minus tc to the power half. So that is nu equal to half. So that's nu equal to half, which is the Gaussian model, and that was the argument. And now I have picked up some correction over here. This is a general argument which is always valid, that it is b to the power 2n, which is 1 over m square over here, and it just turns out that if the m square is going to change to some m prime square, which is what it does at this stage, then the argument would have to go with the m prime square rather than the m square which we have. So over here it is this m square, and now it is and what has happened here is that you have, so this is without this term over here. I have gone to the beyond the Gaussian model, and I have picked up this contribution over here. And therefore, there is going to be a shift from the nu equal to half corresponds to this part over here. There is going to be a change coming from this part over here. And that is the change that we are after. And that change would mean, I have this lambda. Lambda is an unknown quantity, and therefore I need to fix it. So, all right, I look at that. Therefore, I want to look at this graph over here and see that is the first correction that one generates on lambda. And then what you have, that your lambda has moved to some lambda prime, and the lambda prime is given by this expression over here. So that's where we are. Another aside over here, since I have gone to two factors over here, two interactions over here, there has to be, if I want to be consistent in that, I have to, in this chap, I have to have the next order. The next order is one which looks like this. This is nothing but a geometric series expansion of this. But then there is the other, which is this. So this is lambda, this is lambda squared, and this is lambda squared. Now this, they would have, when we wrote out all those expanded terms at order lambda squared, these would have to be there. We ignored them because I already have a correction to the Gaussian at order lambda. I kept only this because the correction to lambda has to be of order lambda squared. So that is why they were, and this chap in particular is very dangerous. So, but anyway, there is a point about it which will. So what do I do? See, all this, the logic has to be that for some reason or other, lambda is small, and that is why I can say that I'll drop this and keep this to the lowest order and get an answer. So what makes the lambda small is the question that we are going to ask. So all right, so what makes the lambda small? The m square, which was the coefficient of this, has the transformation that it is m goes to m prime square, which is b square m square. This one has the transformation to this order that it goes to some lambda prime over 4, which is equal to lambda over 4 times b to the power 4 minus d. M prime square was b square m prime square, m square, and this is lambda prime equal to lambda times b to the power 4 minus d. So long as d is less than 4, the lambda prime grows. Lambda prime is bigger. Over here, b greater than, b is always greater than 1. I have a 2 over here. So that m prime is greater than m was never in question. B is always greater than 1 because b is what I used as cutoff, lambda going to lambda over b, which is a smaller cutoff. So b is always greater than 1. Now it tells me that this lambda prime is going to grow as I do this scale transformation. So lambda prime growing is not such a good thing. So now you look at the correction. The correction is going against it. So the growth over here is going to be checked by the growth over there. All right. Step number 2. So that is what you, what if this b, I want to, this is a discrete process that I'm showing you that essentially I remove b can be a factor of 2, I remove half the spins, or a factor of 3/2 or something or other. I want to make it a continuous process and write b as something which is close to unity. so that B can be a continuous variation. So B I write as e to the power delta L, which is very nearly equal to, B prime. If I write B prime is equal to B e to the power delta L, I mean, over here, that corresponding thing would be, I mean, your M prime would have to be written in terms of, this B, what I meant was that B is a factor which is greater than unity, but I want to write it, I want to make it very close to unity, so I write it as B equal to e to the power delta L. So delta, this, if I write this as this, then the answer is, it is B is 1 plus delta L. If I look at this first part of the equation over here, this tells me then that M prime square over 2 is equal to M square over 2 plus M square over 2 into delta L. M prime square, cancel the 2's, M prime square minus M, so this is delta of M square. If I take this on this side, and this is delta L, and that is equal to 2. Limit delta L tending to 0, dm squared dl is equal to 2. So your relevant, what does it mean? It tells you that M square grows as you carry out this removal of degrees of freedom process. Always, always. So the temperature is always a relevant quantity. By that same token, this one over here says that lambda prime is equal to lambda 4 times 4 minus d. So you call 4 minus d as being epsilon. So 4 minus d is epsilon, and then this is lambda prime equal to lambda into 1 plus epsilon log b. We said e to the power, the notation was delta L. So B is epsilon to the power delta L, which is e to the power epsilon delta L. So this is delta L. Therefore, d lambda dl is equal to epsilon times lambda. And for epsilon greater than 0, which is d less than 4, the lambda grows. So M square grows, that's this chap grows, this chap grows. Only one chap can grow. I mean, there is only one relevant variable in this problem. Relevant variables are those which have to be fixed at 0 in order that you go to the critical point. So this by having h equal to 0, I have h is one of the relevant fields. The other is the temperature. You get to the critical point by setting critical point is achieved for t equal to Tc and h equal to 0. That's the critical point. I already have h equal to 0. So T equal to Tc is what I would have to adjust. So it is the relevant operator, the one which would have to be a growing, is this. This one grows at order epsilon. And then if you look at this one, you see it is going to be cut back. All right. So the d lambda dl is equal to epsilon lambda Minus 9, and then it is lambda over 4, no, lambda square, right? So the 1/4 cancels this, that is that, and I should have had, all right, a lambda over 4 over here, and there is, because that's the coupling constant, and there is a, so there is 36 over here, there is 16 over here, so it is 9/4. And then there is this integral which goes lambda by b to lambda ddp over p square plus m square whole square. Yeah. Now see the game. So dm squared dl is 2. That's from this. Next term says dm squared plus dl, dm squared dl has to come from here, right? So let me write things at this point over here. D two-term accuracy, dm squared dl is 2 dm square dl is 2 plus 3 lambda by 2 integral lambda over b to lambda ddp over p square plus m square. That's dm square dl. Well, I would, I mean, to write it as, you see over here, there has to be, I mean, you have to extract essentially the delta L proportional part. I mean, this one, B is 1 plus 2 times delta L. So there would be a part over here which is proportional to delta L when I work this out. So this is the delta L part of the, which I would be interested in, which would go into the denominator over here, just as the delta L did over here. And that is what, that's the game. D lambda DL. D lambda DL is epsilon lambda over 4 minus lambda square times something, which is going to be, I mean, some integral over here. My goal is to do perturbation theory. So my goal is, right now, I'm at a total loss. I have developed diagrammatics, I have, but I don't know what lambda is. This lambda over here can be 100, can be 1 over 100, who knows? So it's not a trusted quantity for what? But where do I need it? I need it at the fixed point. I need it when I have done this procedure infinitely many times and things have moved to a fixed point. So I need it at the fixed point. Fixed point would mean that lambda DL, because there is one relevant operator that does not, that reaches a fixed point which is infinitely far away. So dm squared dl is equal to 2, so that just keeps on flowing. Everybody else reaches a fixed point, either 0 or non-zero. This chap over here, d lambda dl, has the potential for reaching, because this first term is positive, next term is negative, d lambda dl has a fixed point which is lambda the fixed point lambda star is epsilon divided by something or other. Correct? I can set up a perturbation theory if epsilon is small. So perturbation theory possible, perturbation theory for d less than but close to 4. That is why the perturbation theory in this context came to be known as an epsilon expansion. Get the point? So that is how this d equal to 4 magically appears. Everything is done around d equal to 4. We knew that d equal to 4 is a magical dimension because the dimension of lambda, the naive dimension of lambda is d minus 4. So under a rescaling transformation, lambda grows when it is d less than 4 and goes to 0 when d is greater than 4. So d greater than 4, the thing is entirely a Gaussian model. So Gaussian model holds for d greater than 4. For d less than 4, this term is important, but it turns out that it is weak because the fixed point value of lambda is proportional to epsilon for small epsilon. The corrections would be epsilon square, epsilon cubed, and so on. And that therein lies the perturbation theoretic approach that I have generated out of nowhere a perturbation scheme. Just played around with the spatial dimensionality to make, and that is why, I mean, 50 years ago, this was a revolution. That you, everywhere else, if you did QFT, in QFT, electrodynamics, ready-made coupling constant, E squared by H bar C, 1/137. Strong coupling can't do anything. So electrodynamics works, weak coupling works, weak interactions work, strong interactions don't work. Period. Here comes a situation where it is strong interaction, you play around with the dimensionality and you find that there is an expansion parameter. That was the game changer. Thereafter, the other branches of physics followed that you could now be searching somewhere else. It's not the strength of the interaction. You don't care whether this lambda is big or small. There is, you can define under this various circumstances a way, a lambda, a coupling constant, which can be effectively small and possible. I mean, you may not have a God-given small parameter. You don't need to have a God-given small parameter in the problem to do a perturbation theory. That is the big thing over here. So, great. Does it? How well does it work? So, let's do that part quickly. I mean, it won't. Quickly is always on the board, not so quick. But where is the other? Not there. Oh. No, this is also the wrong kind. I thought there was the right kind. No, no right kind. All right. It's all right. So, all right. What will I calculate? There has to be a real thing which I want to calculate. I'll calculate this exponent nu, which is the easiest. The exponent nu is going to be given by I managed to get that out. It is nu is it's psi of b times I scale by m square is like t. So I take psi of t and then I make it b of t, and this psi of t has to be, original one has to be bigger by a factor of b, right? B is the scale factor for, I mean, this is it, the m prime square going, that is like t. So t is, this is b, so t goes like b squared t, right? So t is, t goes to b squared t. This is m prime square, so that is t prime. So t, this is d prime over here. You have gone, the correlation length at t is bigger, so related to this, which is equal to b to the power n xi to the xi of b to the power 2n by t. B to the power 2n times t is of the order unity. 2n is equal to log 1 over t by log of b. So n is, this is n is, so xi of t b to the power 2n, n is log 1 over t log b. So b to the power n over here, so log of b to the power n is equal to half log 1 over t. So this eventually, when this has become unity, is going to be log of 1 over t to the power half times a number. So xi 1 over, no, not the log. What happened? I want this as b to the power 2n equal to 1. It is n, it has to be 1 over t to the power half, right? It is 1 over, no log here. The logs go away. It is b to the power n. This is equal to log of 1 over t to the power half. So b to the power n is like 1 over t to the power half. So xi of t goes as, so xi of t is proportional to 1 over t to the power. So that's the what the correlation function is doing. So it is this b which is over here, or this b squared. I mean, t goes to b squared t. So t going to b squared t, it is a question what this term is going to do for you is it's going to modify b squared into something else. And that is what you are supposed to find. So you are in the business of evaluating this term over here and getting what correction effectively this term has to correct this term over here, and what is the correction. So that is what the game is all about. So very good. But I need the lambda. That's my problem. I need the lambda, but I know what lambda is. I want lambda to be the fixed point of this equation. So that is where the lambda is going to flow. What does the M flows to is a situation where it is flowing far away, infinitely away from the critical point, and you are getting the infinite length scale out of it. And this is flowing as you reach the critical point. This is flowing infinitely too, but after an infinite number of flows, it ends up at a fixed point, which is this. So comes down to calculating this integral. Where will I calculate the integral? This is already of order epsilon, and there is a lambda. If you look at this, this is saying that lambda has to be, the fixed point is d lambda dl equal to 0. So lambda has to be of order epsilon, right? So lambda has to be of order epsilon, and therefore this term over here is you are going to you evaluate. This is already of order lambda square, which is epsilon square, and therefore now for the rest of the integral, you can just ignore the fact that epsilon is finite and set epsilon equal to 4. This integral can be evaluated if I want only the leading order of lambda in epsilon. I can go ahead and evaluate this at order just at epsilon 0, which is at d equal to 4. So perturbations theory, when I do this perturbation theory and I'm calculating the integrals, as all integrals will come successively higher powers of lambda, and the integrals therefore are to be evaluated at epsilon equal to 0. This will already carry your epsilon square, so you don't have to worry. And this is going to be the integral at evaluated at epsilon equal to 0, which is at d equal to 4. So I write d lambda dl. D lambda dl is epsilon lambda over 4 minus 9 lambda over 4, and then it is lambda over b to lambda, and it is d4p divided by p square plus m square square. But p is m goes to 0. P is big, and because all the p is a big range. So lambda over b is of the order unity. So this is like, and now of course b is even very close to unity. So this is all in the very high. So this is equal to epsilon lambda over 4 minus 9 lambda over 4 lambda over b to lambda d4p divided by p to the power 4 equal to epsilon lambda over 4 minus 9 lambda over 4. If I call the angular integration, let's say, gives me S4, the surface area of the 4-dimensional unit sphere, and then I'm left with p cubed dp, so that's dp over p, so it is log lambda divided by lambda b, so it is minus lambda square. So d lambda dl is this. So this is d lambda dl is this. The lambda equal to 0 is an unstable fixed point. There are two fixed points over here. Lambda equal to 0, it's an unstable fixed point for epsilon greater than 0, which tells you that it will flow to some lambda, will flow to some constant value, non-zero value. Epsilon less than 0, this is lambda equal to 0 is a stable fixed point, and lambda flows to 0. all higher order terms are unnecessary. But here it is lambda star is equal to epsilon by 9s4 log b. So that is where you flow. So lambda square equal to epsilon divided by 9s4 log b. Now you can put this in and over here and make sure that this is going to be stable so far as lambda goes. It's a stable condition. That is, you can just carry out the linear stability analysis. That is d delta lambda. So you write lambda star plus delta lambda and calculate ddl delta lambda, and you will find that this side is negative. So lambda, for lambda itself, this is for the flow of lambda, this is a stable fixed point. But in the big scheme of things, it's an unstable fixed point because m is going to flow away. So the critical fixed point is unstable, but unstable in only the relevant directions. The relevant directions are the temperature and the magnetic field. All of the parameters that I have put in are not relevant for the critical phenomena, but lambda has the special feature that lambda acquires a non-zero value. So it controls the critical phenomena. If I had terms which are like mu times 5 to the power 6 or something to the power, all those, because of this 4 minus epsilon that you see, 4 minus d that you see, would all flow to 0 for d greater than 4. So d less than 4, I have this chap there, and therefore I have a, so the fixed point value is this quantity over here and that. All right, so now what? Now what about this chap? So this is equal to, this has m prime square is this b square m square. So this is dm b is this e to the power delta L. So m prime square by 2 is equal to m square by 2, 1 plus 2 delta L. And then this is 3 lambda by 2. And then it is lambda over b to lambda. And now the lambda is, I know, is going to be of order epsilon. So this is a small term. I will evaluate the rest of it at d equal to 4. So this is d4 p over p square plus m square. So this is equal to m square by 2 into 1 plus 2 delta L plus 3 lambda over 2 S4 coming from there, and it is d cubed, p cubed dp. So p cubed dp divided by p square plus m square going from lambda over b to lambda. And this is p square times p dp. So this is equal to, so if I just focus on this part over here, this is 3 lambda by 2 S4, and then it is p square, you put a 4 over here, and it is a p square dp square over p square plus m square, which is equal to 3 lambda over 4 S4, and then it is P square plus M minus M square. So P square plus M, this part is lambda over B to lambda. It gives me gives me lambda square minus lambda square over B square. That's the part which comes from here, which has no parameter, which does not have any M square, but the other term is minus M square. Don't need this one, right? Good. So minus M square, and it is plus M square minus M square, and minus M square lambda over B to lambda, and it is D of P square over P square plus M square, which is equal. So this is equal to 3 lambda over 4 S4 lambda square 1 minus 1 over B square minus M square, and then it is log of P square plus M square divided by that. So that is lambda square plus M square divided by lambda square over B square plus M square. Here. A 3 lambda right. So what has happened to that M? Now, obviously, M square is much smaller than M square tends to 0. So this and this, they don't. So this is this. So it is just ln B square. So, right, you can get rid of this now. Get rid of this part. So I will. Now, what is lambda? Now, lambda is to be evaluated at lambda star. Lambda star is epsilon over 9S4 log B. And so you are going to pick up from here. So I'm focusing on this term. You're going to write, so M square. So I get rid of the 2 from here, the 2 from here, the 2 from here, the 2 from here, the 2 goes from here. This becomes 2. So this becomes a 2, and then this becomes a 2, and this becomes a 2. Correct? All right. So here we are, dm square dl. So that is, and then is 2m square. 2d is 2m square. And now I'm picking up a correction there. I'm picking up a correction there, which is this term over here, which is minus 3 lambda S4, and I have removed the 2. So I have removed the, so I have removed the 2. Right? I mean, have I removed the 2's from here? Is the question. Have I removed the 2's? Well,
ছিল তারপর 3/2 হলো
4 ছিল, huh? 4, so 2 সরেছে. Very good. All right. So then it is this times your 3 lambda S4. So this is by 2 and m square here and log of b square. Log of b square, but b square is b square is e to the power 2 delta L. So this over here, b square is what I have written as e to the power 2 delta L, right? I mean that b is e to the power delta L, b square is e to the power 2 delta L. So this is 1 log of b square is log of e to the power 2 delta L. So this is 2 delta L. So that cancels the 2 over here and gives me a delta L. Here, that delta L is taken care over here, and therefore I have this, right? So that is the m square part of the term, and then there is a constant term plus a term. I did the second one. So over here also you'll be picking up a 2 delta L, because I mean this is lambda, so this is b square minus 1. So this is going to be like plus 3 lambda S4 by 2, and I have lambda square b square minus 1 by b square, and b square is 1 plus 2 delta L. So this is 2 delta L here, and this is 1 over here. So the 2 delta L gives me a 2. So dm square dl is m square into this quantity over here, and then there is a constant over there. That constant essentially tells you that the critical point is shifted. So this is equal to, but now lambda, what is lambda? Lambda is the lambda star, which has to come from there. And yeah, so what happened to the y of traps? What's that? Somewhere the log b should have been there, and oh God, where? But I have made it a d lambda dl. Shouldn't have had a log b. Log b is e to the, sorry, a d lambda. By the moment I made it a d lambda dl, sorry, it should have taken care. B is e to the power delta L, written down over here. So it is this dl over here removes the log b over here. Thank God. Sorry, I mean I should have this. Yeah. Otherwise the delta L does not. The delta L comes from the log b over there, and that's the. So epsilon over epsilon over 9s4, and therefore it is the fixed point value. So it is at the fixed point value here. There's 2m square. So 2 minus 3 lambda square S4, which is minus epsilon by 3 times m square plus 3 something, the lambda square by 2s4 lambda square. So that is the answer. at the end of this loop. I have taken all correction terms in, that is, I have gone one step beyond the zeroth order theory. So one step beyond the zeroth order theory meant that for this the correlation function, I go this plus this over here, one step. For the interaction term, the 4-point function, I go this plus, yeah. So I go this plus this. So I have gone one step in perturbation theory, and here I have reached a fixed point, which is this lambda star. And over here, the dm squared dl, which was 2 at this stage over here, has now gone to 2 minus epsilon 3 m squared. So the nu, which was 1 over 2 at this point, the nu then after this calculation, the nu is 1 over 2 minus epsilon over 3. But that cannot be, I mean, I'm correct only up to the first order in epsilon, and therefore this nu has to be written as half into 1 plus epsilon by 6. Right. So gamma So the exponent which is most common, nu is if you do light scattering, but just do thermodynamic measurements, it is gamma, which is 2 minus eta times nu is equal to 1 plus epsilon over 6 plus 1. So for the liquid gas system, therefore, which is the primary n equals scalar order parameter, gamma is very nearly 1.16. So you had gamma mean field, MFT was 1. The first order epsilon expansion is 1.16. The real answer almost 1.236, something like this. If you do a second order correction, which is not very, it's a lot of entirely along these lines, but just a lot of calculation. And you would be picking up something which is very close to that. But that is, I mean, now if you do a third order, you go away. Because these are not convergent expansions. I mean, although I have picked up artificially a small parameter in this problem, and I have done perturbation expansion with that, it is guaranteed to do better at the first order. You are lucky if it does better, even better at the second order, but at some point your luck has to give out, and it gives out at the third order in this calculation. So these techniques where you sort of generate artificial expansion are extremely useful, because the mean field theory was not a correct description of what was going on. The fluctuations are very important. You have taken them into account, and you have got an answer at the first go, which is trustable as going towards the right answer, and a long ways towards the right answer. The fact that over here the second order works is lucky, but I mean, all right. But at the second order, what is important is that you also pick up the anomalous dimension, which is this eta that you see that the even if you are at infinitely big correlation length, you don't see the scattering intensity, light scattering should go as 1 over k squared. That's expected if xi, the correlation length, goes to infinity. But you don't do that. You go as 2 minus eta. So this exponent, which is of the order of 0.035, is not so easy. If I go to the next order and consider this diagram over here, I'll pick up the first correction to eta, and the answer is epsilon square over 54. So you pick up about 0.02. This 0.35 is what you get. There's a scaling relation, gamma equal to 2 minus eta times nu, and gamma can be very accurately measured. Nu can be accurately measured. That is what gives the indirect eta as something like 0.035, somewhere between 0.035 and 0.04. So this is, the first appearance is at a two-loop diagram. So the diagrams, the perturbation theory is generally classified as one loop, two loop. This is the one loop, this is one loop. Here is the two-loop correction. At two-loop order, you are looking at 0.002 or slightly less, 1 over 50. And I think earlier this year, somebody did the 7th loop, and and comes pretty close to that. Yeah, they have these numerical algorithms for doing these integrals. So, so it's, the game started in early 70s, so 50 years to go from 0.018 to somewhere close to this. All right. This is essentially the perturbation expansion is non-convergent. Yeah. So for some people, it's a craze that I know that it, but if I really push it to higher order, will I go somewhere close or not? That's, otherwise, it's not that people are off, but there remains a hardcore group. And then maybe you might find that at some decimal place, it's not right.
It's because of the mathematical structure that it's not convergent. That's the one.
Yeah. And if it really turns out that this goes off, then at some point or other there could be a bigger malaise sitting somewhere. So for some people, it's a game which they are good at playing. And doing this, it's a dedicated job, as you can understand. And fine. All right. So this is it. Enough spoken on this. We have spent a lot of time. I do hope that you will independently go through the steps. The place where it's done in great details is schema, Modern Theory of Critical Phenomena, which is more than 50 years ago. but that came in 1973, I think, 73, 74, something like that. So this is where, actually the nuts and bolts of all these, what you saw, the nuts, that is what you find over there. There were lots of lecture notes of the late 70s and early 80s. So that's where, if you scan this region, you would, this period in time, if there are things which are archived, you would find lots of people. That's when it was popular and it had to be taught and so on and so forth. So, but as things progressed, you didn't. The method of doing the calculation changed, and all right, it's not, but the philosophy remains. The next big thing is that this comes from 4 and goes below. The next thing is you start from 2 and go up. And so d equal to 2 and go up. But this you can't do for the scalar model. You can only do for n, the number of components greater than 2. So this is this, what do they call it? So it's a low temperature expansion. This expansion parameter is the temperature. Just as over here, the expansion strong coupling expansions are what they are called. The expansion parameter, there always has to be a weak coupling, strong coupling. So strong coupling, obviously the coupling constant is not the chap. What is the expansion is done in the temperature. Why the temperature? Because n equal to 2 at d equal to 2, if it is n equal to 2, then the transition occurs at t equal to 0. So finite transition temperature occurs for n equal to 2 if you are above d equal to 2. And so you can set up expansion, set up a perturbation expansion in the temperature. So that is the strong coupling business. All right. So you come from 4 and go down, you come from 2 and go up, and primarily because of interest shifting to lower dimensional things, this kind of an approach is today more pertinent than coming from above. So if you are going to focus on lower dimensions, that's the... Anyway, enough said. All right, so what's the next thing that we want to do? We want to talk about the non-ideal real gas. How much real? Real in the sense that they can undergo elastic collisions. They cannot interact at distances. So that's so much for reality. But and this is not bad really. I mean, because if I take a real gas, so neutral molecules will have interaction. Interactions are all Coulombic. So Coulombic, these are neutral. So VR going as 1 over R is ruled out. So VR can't go as 1 over R. So the next step is that it is a quadrupolar, it's a dipole-dipole interaction. So dipole-dipole interaction, the potential energy has to go as 1 over R to the power 6. So this is point charge potential. This is dipole potential. And when it is all right. Huh? 1 by R2. So this is the dipole potential for a single dipole. This is the for a point charge, right? I mean, the dipole potential is m dot R by R cubed, right? And if I have 2 of these, the answer, 2 of them, the mutual potential energy is m1 dot R into m2 dot R divided by 6, R to the power 6, right? Minus 3 m1 dot m2 by R to the power 4, isn't it? That's the one. So that is, I mean, the yeah. So the mutual that's the dipole-dipole interaction. Yeah. So it's a dipole-dipole interaction at the next order, and that all right. Not all molecules have a dipole moment either, and so you have a 1 over R. As the potential, then you go to a dipole potential. The practical potential that works for most is a Leonard-Jones potential, which is 1 over R to the power 6 minus 1 over R to the power 12. So that's the Leonard-Jones 612 potential. Well, all that apart, what is the most important part of this problem? The most important part of this problem certainly is when they come very close, right? I mean, if I am at a distance, if I am at a largish distance, certainly the interactions are very small. The important thing that I need to worry about, I mean, this should have been the other way. I mean, this is the repulsion, and this is the attraction. Sorry, right? So that's the repulsion, that's the attraction in the Leonard-Jones, telling you that this repulsion, which is where they come and essentially hit each other, is the dominant part. So if I'm going to do a integral over the region surrounding the molecule, this is going to play a far bigger role than that, which you can see in this van der Waals equation. P is RT over V minus B minus A over V square. This is the hardcore repulsion. That's the excluded volume, which takes into account the fact that the 2 centers can come no closer than this. So that's the repulsion part of it. So which is what the elastic scattering would take into account. And that's the strong effect. Then this over here, it's not to say that this is not important, because without it, you wouldn't have the these phase diagram, where these isotherms, right? Isotherms which and then go like this, the van der Waals equation, which tells you there is a critical point, the fact that you go like this would not have happened if you didn't have this term over here. So it's the critical behavior vital. But the point is that to a first approximation, if I'm going to look for a non-ideal gas, then the first thing I would like to do is take the elastic scattering into account. So that is what Boltzmann did. So consider interactions as elastic collisions. So very good. You have to be then at this, the interaction therefore occurs essentially at the same space point. The molecules are essentially point objects in this, coming with a velocity v1 and v2 and scattering off with a v3 and a v4. So that's so they come, collide, and off they go. So momentum conservation, mv1 plus mv2 is equal to mv3 plus mv4. Kinetic energy conservation, half mv1 squared plus half mv2 squared is equal to half mv3 squared plus half. So these are the conservation laws and the number conservation, obviously. So number conservation. So this whole process has 5 conservation laws. So so therefore, so we focus on the. I'll just get started and then we'll finish off. So I focus on a region of. It's all happening in the phase space. So a large RV space, and so happening in the RV space. And you are looking at a box which is, this is the physical box which has a volume d3r, and all the action is going on over there. So now let's say I have all the action going on over there, and let me focus on those molecules with velocity between v and v plus d3v. So it's in the. So I'm focusing on d3r, which is always, and d3v for this class of molecules. So in phase space, a volume which is d3r, d3v, it is always going to be d3r. I don't need to, but the d3v is focusing on a specific class of molecules which are inside this box over here. Physically, they're all within this small box, but physically what is happening, all the events will be happening inside this small box over here. and the changes that will happen will have to be in the changes that I will be noting down would be the changes that are happening to these set of chaps which are living here and whose velocities are between, that is living in this physical box d3r, and whose velocities are between v and v plus dv. And what is happening to them? They are being hit. So they are being hit by molecules which come and hit them with a velocity v1. So how many collisions per unit time? That is what we need to write down. So what this hit will do, it will take you out of, take this V chaps out of their V velocity. So it comes and hits. So the number of molecules that are having a velocity v and are located in this physical box here is going to be FRVT and D3R, D3V if it's. Huh? That's the number. That's the density. So it's a number density of this. So this is this times D3R, D3V is actually the physical number of molecules which are having a velocity between V and V plus dV and are located in this physical box D3R. So they are being hit. So collision with molecules with velocity v1. Now, who are those? Who are the ones which? Where are they? Who can come and hit this set sitting over here? So that can be done. So all right. Now let me focus on this D3R, and I have these V chaps sitting over here. If a V1 chap comes and wants to hit it, then it can only reside. So so I want to focus on cross-sectional area dA, let's say. So sorry. So if they want to come and collide with this, then in unit time, the number of them which will be able to come and hit are those which are residing in the box which has a length v minus v1 and has a cross-sectional area which is the cross-sectional area of this. So it is going to be v minus v1 times delta A, and the number of these chaps are going to be f v1 so that's the physical box size in which I'm looking at molecules which are going to come and hit this and change the distribution function. I mean, kick out these parts. So those are going to come with velocity v1, at the and how many of them would be coming? How many of them would come and be able to have a collision? Those which are in this area, the cylinder which has this volume over here. All those which are residing in this cylinder over here would be able to come and hit this chap, those sitting inside this volume over here. So so collision occurs. So what is these are the numbers which are sitting. What is the number which is coming and colliding? That's the number which is coming and colliding. So the number which is, if I focus on these chaps over here, the number of them which is going to get lost will be proportional to the number of strikes, and all of them strike, and that number would have to be RV1 TV minus V1. So this is the total number of hits. That's the total number of hits that are going to take place for, if I focus on these chaps over here. So that's one part of it. And then you are going to go away. You are going to go away. The V1 and V2 will take you to V3 and V4. So we have to worry about how many of them are going to now, the result of this particular collision, V1 hitting it has to be V and V1 hitting V2 and V3. So V and V1 hitting V are going to take it out into this V2 and V3 over here. So there would be two similar factors which account for the number of this is, so if you imagine that this is what is lost. Now you want what is gained. So you lose this. So you imagine the process. If V and V1 colliding takes you off to V2 and V3, then these chaps with the arrows reversed are the ones which will be producing V. Right? So this is the loss of V. Right? And a similar factor which is F2 times, so this is F1, let's say. So this is F1 over here, and then it is a factor F2 which is R, and there is the V2 which is going to collide with FR and this V3 and T. Inside this volume, physical volume R, a V and a V1 collide, and this collision leads to molecules getting away from these particular molecules, leaving the volume that we are considering. The reverse, so if V and V1 takes you to V2 and V3, then the reverse V2 and reverse V3 will take you to the, So you will be picking up some V and V1 from the collision between V2 and V3. So because it is the, these are now,
number of collisions with molecules total number
hello? কতগুলো কলিশন হবে হচ্ছে কথা। কলিশন তাদেরই, আমার যদি আমি এই ভিটাকে রেস্টে নিই, তাহলে V1 is traveling with v1 minus v, তাহলে সে যদি এই সিলিন্ডারটা একটা সিলিন্ডার অফ লেংথ v1 minus v এর মধ্যে থাকে, এই v1 ওয়ালারা,
আচ্ছা হ্যাঁ
তারা সবাই ওকে, হ্যাঁ, so that is why this factor over here with এই যে কতগুলো না, those living inside a cylinder of length v minus v1, with unit cross, and the cross section is so there would have to be a scattering cross section over here, which is v1 going to v2 v3. So this collision, it's not all of them would take you to, I mean, there has to be for a particular v2 v3, there will be a scattering probability of v and v1 taking you to v2 and v3. So, and there has to be, I mean, for that normal FV, a term which is going to look like. So D3R, there is going to be a D3V1, which comes from the V1 occupation. The D3V is the number which normalizes, I mean, the FRVT comes with a D3R and D3V to give you the number. The F1 comes with a factor V minus V1 and D3V1 to give you the. So in this unit cross section, so this is this volume which physical volume for this one is a unit cross section, and then it is so that's. So this is what the loss is going, and the reverse thing is going to be the gain. I mean, the V2 and V3 going to V and V1 is going to, with V2 and V3 colliding within the box V2 minus V3, and then you write down a similar expression, which we will do next time more carefully, that this is the philosophy, that this is the loss through scattering. Next, to make any progress, you would have to say scattering is elastic. So it's energy conservation is there, yes, and therefore all right. I mean, it's specialized. Let's put it that way. It's elastic collision, and there is the reverse cross section. So there is going to be some loss. There is going to be some gain. This minus that is the rate at which the distribution function of this V is going to change. So I'm focusing on a V, and it is going to be V colliding with V1 and going away to V2 and V3, and then the reverse, where V2 and V3 are going to collide and are going to give you V. So V in, V out. So this is V out, the other is going to be V in, and therefore you are going to have the net change in V in that volume is this minus that. That is the story. So we'll do this, and but this sets the. মানে ফোকাস করছি জাস্ট ভি এর উপর, মানে আমি ফোকাস করছি কার উপর না, যাদের এই বক্সটার কথা বলছো তো, এই বক্সে তারাই আছে যাদের ভেলোসিটিটা ভি এর কাছাকাছি আর যাদের এই ফিজিক্যাল ভলিউমটাই। হ্যাঁ, বক্সটা তো ইমাজিনারি, বক্সটা তো ইমাজিনারি, মানে এই বক্সটা তো ফেজ স্পেসে, মানে এই D3R-টা একটা মানে সেটা একটা রিজিয়ন অফ ফেজ, মানে দ্যাট ইজ দ্য এই ঘরের মধ্যে যে কোনো একটা জায়গা হলো D3R, রাইট? আর এবারে ওই রকমই একটা ভেলোসিটি রেঞ্জ যেটা আমি দেখতে চাই সেটা আছে D3V. So this is the phase volume for all molecules which are within the physical box D3R and whose velocity lies in this velocity box over here. So a boxটা কিন্তু 6-dimensional space. So সেই 6-dimensional space এই ধাক্কাধাক্কিটা হচ্ছে, and yeah, মানে মানে ধাক্কাধাক্কিটা হচ্ছে 6-dimensional space, কিন্তু মাইন্ড ইউ তুমি বেরিয়ে যাচ্ছ কেবল ভি স্পেসে। ধাক্কাধাক্কিটা কিন্তু মানে অল দ্যাট ইউ আর কনসার্ন উইথ হচ্ছে ওই কোন পয়েন্ট, মানে আমার এই মলিকিউলস গুলো যেখানে, যেটা এইখানে যদি আমি একটা D3R বক্স কল্পনা করি, এই ফিজিক্যাল বক্সটা, what I am asking for is যে এই বক্সটার মধ্যে যাদের ভেলোসিটি হচ্ছে V1 তারা V2 ভেলোসিটি যাদের, তাদের সাথে কোলাইড করলো, রাইট? সো যদি আমি ওকে ফেজ স্পেসে আঁকতে চাই তাহলে ওটা একটা 6-dimensional স্পেস যার 3 ডাইমেনশনে 3টে স্পেশাল ডাইমেনশন দিয়ে একটা বক্স তৈরি করা হচ্ছে যেটা আমি ভিজুয়ালাইজ করতে পারছি। আর এই বক্সের মধ্যে যে ফিজিক্যাল বক্সটায় যে মলিকিউল গুলো আছে তাতে সব রকমের ভেলোসিটি আছে, তার মধ্যে যাদের ভেলোসিটি ভি এর কাছে তারা আবার মানে দ্যাট কনস্টিটিউটস আরেকটা মানে ওই মানে একটা 6-dimensional স্পেসে তাহলে 6টা লাইন তৈরি হলো, মানে এখানে যে মানে 6টা লাইন আর মানে হোয়াটএভার, মানে যেভাবে ইউ ড্র মানে ওই দিস, এটা 3-dimensional রিজিয়নে আর ওটা একটা 6-dimensional রিজিয়নে বাউন্ড, রাইট? সেই 6-dimensional রিজিয়নে ওদের মানে সংখ্যাটা যে এই ফোকাস এরিয়াটা হচ্ছে এইটা ইন্টু এইটা, আর তার উপরে যদি আমি ফোকাস করি তাহলে কথা হচ্ছে যে মানে V2 V3 ওয়ালারা ওই ফিজিক্যাল এই বক্সটার মধ্যে, হ্যাঁ ফিজিক্যাল এই বক্সটার মধ্যে যে V2 V3রা এসে ওকে ধাক্কা দিল তারা মানে হচ্ছে দ্য রিভার্সটা, মানে V2 V3রা ওই বক্সে এসে ধাক্কাধাক্কি করলো আর V1টাকে ইয়ে করে দিল, মানে অবভিয়াসলি D3V D3V1 সেটা ইজ দ্য সেম অ্যাজ ইলাস্টিক কলিশন হলে পরে অ্যাজ D3V1 D3V2, সো সবকিছুই ওই একটা বক্সেই হবে, রাইট? কিন্তু টেকনিক্যালি আমি ইন জেনারেল যদি ইলাস্টিক নাও হতো তাহলে আমি এই লসটাকে যদি এই লিখি, গেইনটাকে আমাকে লিখতে হতো V2 minus V3 D3V2 D3V3, রাইট? কিন্তু ইলাস্টিক কলিশন হলে পরে ওই d3v1 d3v is the same as d3v2 d3v3 জ্যাকোবিয়ানটা মানে
তাহলে মানে এখানে আমি কোটেশন ছিল ভেলোসিটি ডি পার ইউনিট টাইম আমি এখান থেকে ক্যালকুলেট করব মড v মাইনাস v1 আর ডেল্টা অফ ইট এন্ড এরপরে আমি এটার সঙ্গে এইটাকে মাল্টিপ্লাই করছি নাম্বার অফ পার্টিকেলস উইথ ভেলোসিটি v ঠিক আছে আর তারপরে আমি ক্রস সেকশন বা মাল্টিপ্লাই করছি জাস্ট বিকজ কি মানে তোমার আপনার কত পার্টিকেল
হ্যাঁ কত এফিশিয়েন্ট অফ দ্য কত এফিশিয়েন্টলি ধাক্কাধাক্কি হচ্ছে
আর ওটা আমাদের লস অফ দ্য পার্টিকেল
এটা হচ্ছে লস কারণ ওই vv1 goes to v2 v3
আচ্ছা আচ্ছা ঠিক আছে আচ্ছা স্যার দুটো নাম্বার অফ পার্টিকেলস কে মাল্টিপ্লাই কেন করেছে
because I have assumed the particle velocity v and velocity v1 are uncorrelated. Yeah, very good. That is you are assuming what Boltzmann called molecular chaos. No relation between v and v1. So no correlation. And therefore independently এরা এসে একে ধাক্কা with no মানে এরকম নেই যে এমন কোরিলেশন এফেক্ট আছে কেউ বলবে যে না এই সবগুলো সব v1 গুলো মারতে পারবে না so yes that's vital যে এইটা times এইটা করে দিলাম which means যে v and v1 velocities are totally uncorrelated মানে ধাক্কা মারছে একটা মোমেন্টে কিন্তু দ্যাট ইজ ইট মানে আমি এইটাকে চালিয়ে ওটাকে ধাক্কা মারি যদি ওই বক্সটা মানে ফাইন আই মিন देयर इज नो कोरिलेशन बिटवीन देम so vital yeah যে v আর v1 uncorrelated so তাই জন্য গুণ করতে পারছি
f of r v and t ওটা হচ্ছে নাম্বার ডেনসিটি অফ পার্টিকলস তো that means that into volume that into d3r number of particles আচ্ছা তাহলে d3v টা
d3v টা এইটার জন্য মানে এই d3r d3v ফেজ স্পেস রিজিয়নে আমার FRVT হচ্ছে the density
density of particles
right so d3r d3v comes automatically that is the number of the RV variety
মানে এটা density of F হচ্ছে density of particles
এটা হচ্ছে the number of particles in this volume d3r d3v having velocities r and v মানে having position
মানে এই f into d3r into d3v টা হচ্ছে number of particles with that ঠিক আছে
আর এসে মানলো কারা না a with the d31 আর এর ফিজিক্যাল ভলিউমটা কোথায় না ফিজিক্যাল ভলিউমটা হচ্ছে কারা এসে মারতে পারে না লেংথ হচ্ছে v minus v1 আর একটা ক্রস সেকশনাল এরিয়া আছে which is essentially মানে you assume যে মানে there is a hidden dA somewhere over here মানে ওটা you just set it equal to unity মানে unit area মানে you are considering unit area ইয়াতে মানে কারণ একটা ডিএ বসালে পরেও সেটা মানে ওটা জাস্ট কেটে যেত
আচ্ছা আর ইন্টিগ্রেটেড লস অফ যেটা লস এট পার ইউনিট টাইম বের হচ্ছে তো
at a particular time
particular
huh
particular time per unit.
No, particular time. So at a particular time, this is the rate of loss. Rate, a rate loss হচ্ছে। মানে there will be a delta t. মানে if I write এইটাকে as মানে I'm writing the, all right, if you want a delta t, you just put a delta t. In that case, the loss minus gain is a delta f.
না আমি কনফিউজ করছিলাম জাস্ট বিকজ এখানে v into dA আছে which is volume divided by time ঠিক আছে
volume divided by
মানে v into dA আছে mod of v minus v1
ওই ডেল্টা এটা হচ্ছে this physical মানে ক্রস সেকশনাল
ওটা এরিয়া ঠিক আছে ওটা ওখানে ওটা লেন্থ স্কয়ার আর এটা হচ্ছে লেন্থ বাই টাইম তো l কিউব বাই টাইম ঠিক আছে আর ওটা তাহলে ওটা হচ্ছে f টা
এইটা যে তাই জন্য পার ইউনিট টাইম এই জিনিসটা
এটা পলিজন পার ইউনিট টাইম ওখানে ওর টাইম মানে ওটা উপরে একটা ডিগ্রি থেকে মুভ করতে হবে ওটা পার্টিকুলার টাইম করার জন্য
রাইট আর তারপরে আমি ডেল্টা এফ টাকে ওই ডিটি টাকে দিয়ে ভাগ দিয়ে দেবো আর ডিএ টাকে মানে ডিএ টা is physical area, so it is per unit that yeah মানে এই এটা তো হচ্ছে একটা ফিজিক্যাল ভলিউমের লেন্থ ফিজিক্যাল ভলিউম হ্যাঁ সো ফিজিক্যাল ভলিউম যার এইটা হচ্ছে মানে ক্রস সেকশন আর এইটা হচ্ছে সেই ভলিউমে যারা আছে তারা সবাই কোলাইড করবে রাইট সো ডেল্টা এ টাকে আমি একটা মানে দ্য ডেল্টা এ ক্যান বি দ্য সেম মানে আমি ওটাকে পার ইউনিট ক্রস সেকশন করে দিতে পারি রাইট সো তাই জন্য ডেল্টা এটা ইজ নট ইম্পর্টেন্ট মানে ওটা স্পেকটেটর ঠিক আছে না ও
মানে স্যার এই আপনার এখানে এইটা কিন্তু আপনার ডিগ্রি v1 করলে ঠিক আছে তাহলে আমার টোটাল নাম্বার অফ পার্টিকলস per unit time with velocity v1 collision
yes
এটা মাল্টিপ্লাই করেছি নাম্বার অফ পার্টিকলস with এইটা আর এইটাই ডট করে দিচ্ছি
যেটা আর কি ওই সো রেট অফ লসে চলে যাবে ওই ডিটিটা রেট অফ লসে যাবে